Hello friends. Come, let's look at the wedge block problem, the one where even the sharp students slip. They confidently write n equals m2g cos theta. And, stop right there. Because that, my friend, is the trap. Here is the one thing almost everybody misses. This inclined plane is not standing still. The wedge is smooth, and its mass is m1, the little particle resting on it has mass m2. As the particle slides down, it shoves the wedge, and the wedge itself accelerates to the left. Let's give that acceleration a name A. Okay, step 1, and don't panic. We always take one body at a time. So first, just the wedge, all by itself, and we draw its free body diagram. You've been drawing free body diagrams since class 11. Same skill. The only new twist here is that the wedge itself is accelerating, so we can't just assume the old answer. Its own weight, m1g, pulling straight down. The ground underneath pushes it up, that's n1. And the particle sitting on top presses back on it with a contact force, N, into the surface. Newton's third law, remember? Now watch carefully, we break N into two directions. The angle right here is theta. So straight down it gives N cosine theta, and sideways, horizontally, it gives N sine theta. Keep your eye on that horizontal piece, that's the one that matters. And since only that horizontal push drives the wedge sideways, the wedge equation is beautifully simple, m1a equals n sin theta. One equation in the bag. But wait, how do we actually find n? If we watch the particle from the ground, it's moving sideways and downward at the same time. Two directions to juggle. Messy, isn't it? So let's be clever, and change our point of view. Let's hop onto the wedge and ride along with it. From here, the wedge's own frame, the particle only slides along the incline. Just one direction now. So much nicer. So let's isolate the particle and study it. So what acts on it? Its weight, m2g, pulling down. The normal, n, pushing away from the surface. And because we jumped onto an accelerating wedge, we must add a pseudo force, m2a, pointing to the right. That's the little price we pay for riding along. Now, what exactly is a pseudo-force? It's just a fictitious push we add so that Newton's laws still work while we ride an accelerating frame. A bookkeeping trick, nothing more. Alright, let me set up axes that match the incline. This dashed line, x prime, runs straight down the slope, and y prime points out, perpendicular to the surface. Trust me, choosing these axes is what makes the whole thing easy. Now, you might be wondering, where does this angle theta keep coming from? Great question. Let me prove it for you, right here on the side. Look, the incline makes angle theta at its base. That's our starting angle. The weight points straight down. The normal points out, at a right angle to the surface. And here's the little trick, if two lines are each perpendicular to the arms of an angle, they carry that same angle between them. So the weight sits exactly theta from the perpendicular. Same theta, see? So back on our diagram, the weight splits neatly. Into the surface it gives m2g cos theta, the cosine, because it's the near part of the angle. And down the slope it would give m2g sin theta. Now the pseudo force. M2A is horizontal. And since the incline itself is tilted theta from the horizontal, M2A sits theta from the surface too. Same idea, just rotated. Its part away from the surface is M2A sin theta. And N? Well, N is already perpendicular, nothing to split. Lovely. Let me clear the working and keep just what matters. Now let's just add up everything perpendicular to the surface. N plus M2A sin theta must balance M2G cosine theta. And there it is, our second equation. Now, along the incline the particle really is speeding up, that's its relative acceleration, AR, straight down the slope. But perpendicular to the surface? Nothing moves. It stays zero. And that, friends, is exactly why our perpendicular equation works so beautifully. And now, my favorite part. We've got two neat equations, and two unknowns, N and A. So let's eliminate N, and go hunting for A. Take equation 1, and just make N the subject. N equals M1A over sin theta. A simple rearrangement, nothing fancy. Now slide that into equation 2, everywhere we see an N. And to get rid of that ugly fraction, we multiply every single term by sin theta. Watch how nicely it tidies up. Now look closely at the left side. A is hiding in both terms. So we pull it out. We factor it. And there's our bracket, all tidy. And one last step, divide across by that bracket, and out drops our answer. A equals M2G sine theta cosine theta, over M1 plus M2 sine squared theta. Isn't that clean and satisfying? So please remember this, friends, the normal reaction is not some formula to memorize. Every single time contact meets acceleration, you calculate it fresh, from scratch. And be careful in your exam, the paper setter has quietly placed a wrong option for each little mistake you might make. So don't walk straight into the trap. So here's your exam pearl, the single line to carry out of this video. So keep your free body diagram clean. Choose a smart frame. And write only the equations you truly need. Do that, and physics stops being scary. Keep practicing, friends, and follow at Physics or DX.